So our final lesson in chapter 2 is about, well, we're going to start with linear inequalities, but then nonlinear inequalities, specifically quadratics and rational functions. It can be tough. I'm going to show you two different methods, and I'm not going to require you to necessarily do both methods, and sometimes one method works better than another, and sometimes it depends on whether you can use a graphing calculator or not as to which method you want to choose. The idea is if I have a polynomial inequality, so any polynomial, but instead of being set equal to 0, it's going to have a greater than or less than or greater than or equal to or less than or equal to sign. So basically, I'm asking you, where is your polynomial function positive versus where is it negative? Or sometimes when is it equal to 0 as well, in addition to the positive or negative. So we're going to be writing our answers in interval notation. I personally feel like if you have a graph or a picture of the polynomial, that's the easiest way to approach it. But, maybe you disagree. So we're also going to show you what a sign chart would look like. So your note starts off with the definition of a polynomial inequality. And your book and some previous teachers of PreCalc have really encouraged what we call a sign chart as the method that we use to write the intervals. So the first example we have here is a quadratic polynomial. And originally it has a greater than 3, but we know you can't really do anything with a quadratic or any higher level polynomial unless it is compared to 0. So we get it in standard form, and then we factor it just like we would be solving it. And the question is, x plus 3 times x minus 6, when is that quadratic greater than 0? So this is a little sketch or it's a snapshot of a picture of an old graphing calculator. And I'm asking you, where is your function greater than 0, meaning where's your function positive? So this is where your function is positive, here and here. And then everything down here, this is all the negative values for your function. And notice it doesn't say or equal to 0, so we're not going to be including the actual zeros of the function themselves. Which brings me to the most important parts of this problem. So the point in your polynomial for which it changes from a positive function to a negative function is the 0, because the x-intercept is where it changes from positive to negative. So if you could figure out who these zeros are, which you kind of already did because you factored it, that's -3, and this one here is 6. That tells you the boundary for where your function is positive versus negative. So interval notation, I have a positive function from negative infinity until I hit -3. That would be this part here. And then it picks up again from 6 to infinity. Now the other method for writing this, and you can't really see it because my webcam is over it. This is called a sign chart. So you write a little number line and you put your important values somewhere in the number line in relative order, so -3 and then 6. And then if you choose to plug in values into the original function that are to the left of -3, so like they decided to test -4. In factored form or in regular form, in standard form, it doesn't matter. You end up with positive outcomes. And then if you plug in a number between -3 and 6, which I always, if possible, I plug in my favorite number, 0. You end up with negative values as your outcomes. And then anything bigger than 6, when you plug them in, you end up with positive outcomes again. So this is another way to indicate for what interval do you have a positive function versus a negative function. So greater than 0 would be from -infinity to -3, and then jump over all this stuff that's negative, and then from 6 to infinity. All right. So the benefit of doing the sign chart notation is that it's kind of already in domain interval notation order. So you don't have to think real hard about what the interval notation is. And remember, some of us confuse domain interval with other things. So those are the intervals for which the function was positive. This particular one here, if we graphed it or did the discriminant, we'd find out that there's no real zeros. They would have imaginary or complex zeros. So since this function is always up here in the positive region, it is always positive. So when it says, when is your function less than 0, never would be my answer there. So there is no such interval for which it's less than 0. That was fun. All right. These are examples that I think are in your textbook, but not necessarily in your notes packet. But this, these are good problems to go through. So it looks like some awesome person, my coworker, already went through and got some screenshots on this polynomial. we use a little technology assistance, and this cubic function looks like this, where they found out that there is a 0 at 3, at -1, and then also at -2/3. It does not bounce right here. If we got a little better, oh, there's another one, -0.8. Oh boy. Oh no, I don't know what that is. Anywho, I'm only looking for my zeros. This -0.8, 0.304. Oh, I know what that is. I bet that's when they plugged in some numbers. Just they're trying to show us that it gave us a positive outcome. Anywho, um, knowing my students this year, I think they might like the sign chart method the best. So if I take all those x-intercepts, all those zeros, and put them in, relative order, the first one that I would have hit was the, let's see, -1, and then -0.67, which we know is -2/3, by the way. And then 3. So it's a little difficult to tell what's happening over here, but I can definitely say for sure that once I go past -1, I was getting negative values, because see how it's below the x-axis down here? So then it must have popped up above the x-axis between -1 and -2/3. And then it's going to dip back down below that x-axis right here. Okay, and then it pops up to a positive function again after 3. So I kind of figured out what the whole point of this question was. They want to know when it's less than or equal to 0. So they want to know all my negative components, but remember also equal to 0. So when we get to the parts where they actually do equal 0, we're going to be using brackets. So the interval was from -infinity to -1 with a bracket, union, and then let's see, -2/3 to 3 with a bracket as well, because it does say equal to 0, so those would be solutions in this case. Oh, then they wanted me to check on the graph. Cool, totally did it. All right, so this one is all on us. They want us to solve this. Good news, it is a quadratic. Even better news, it's factorable. Oh no, it's not. What am I thinking? It's not factorable at all. I have a feeling when we graph this, we would see that it does have 2 real solutions. So if you weren't sure what to do, unfortunately they're not pretty. I thought it was factorable for a minute. We're going to have to use quadratic formula. So opposite of b plus and minus square root b squared minus 4 times a times c all over 2a. So solving for my zeros of this polynomial, I get 3 and then plus the square root of 17 and 3 plus minus the square root of 17, both of them over 2. So me personally, I like this method. I don't really care what it looks like necessarily, but I can definitely tell you what these two numbers are now. This one here is 3 minus square root of 17 over 2. And this one here is 3 plus square root of 17 over 2. And if they want to know where your quadratic is less than 0, that's a really fancy way of saying negative. So they're looking for this interval from here to here. So that would be from not including 3 minus the square root of 17 over 2 to 3 plus the square root of 17 over 2. So sign chart people, you would have done the same thing, except you would have had, oops, yeah, yuck. All right, your 2 irrational answers here, which without typing in a calculator, like I can give you an estimate for what they are. Square root of 17 is like a little more than 4. So 0 is somewhere in between here, right? Because this is negative something little and this is positive. So 0 would be in the middle part here. I would test something like really obviously to the left, like -5. And then off to the right here, I would test like positive. Oh no, I should be careful here. Yeah, +5 would be fine. Here's the thing. The function's going to alternate from positive to negative, and I can tell because it has 2 different zeros. So once I figured out that it was negative in this middle chunk, then I knew it was positive, negative, positive. Like the days before we could use graphing calculators, you had to kind of come up with these little short tricks, but you guys are probably going to cheat on these. It's not cheating. Using your resources. Okay, this next one is totally factorable. That's wonderful. Turns out the factors are little twinsies here. This is going to be a case where your polynomial, your quadratic, bounces up the x-axis at -1. If I can graph. Gross. All right. So remember what happens here, guys, is it touches, like tangent to the x-axis and bounces off. So when I say, when is your function greater than 0, we have to be careful because at this point right here, at -1, it does equal 0. So the interval for when it's greater than 0 is everything except for actually 0. So in order to indicate that, I'd be -infinity to -1, jump over -1, pick up on the other side of -1 to infinity. That's probably a shortcut way to say it, but whatever. That's what your book wants, so that's what I'll do. Oh boy, this next one. A cubic polynomial. Now, if you get it in standard form by, subtracting the 12 over and leaving it as greater than 0, spoiler alert, this is what it looks like. So I can tell from my graph that we have some nice zeros. Looks like there's one right here at 1. Then -1, -2. There must be a nice one right here at -3. And then there's the following one here at -4. Which I could use many, many methods. If I didn't have a graphing calculator and I had to figure out my possible zeros, do synthetic division to find them. I hope I don't ever make you do that. If I do, I'm sorry. But, you could do it. Anywho, not worry about that for now. Using my sign chart, if you don't mind. Since I already kind of have a picture, I'm going to halfway cheat, if you don't mind. So -4, -3, and 1. I can see from my picture here that on this side of -4, my function is below the x-axis, so it's a negative function, and then it pops above the x-axis, so it's positive, and then it's negative again, and then it's positive again. So when is my function greater than 0 would be here, and then here, but notice it doesn't say equal to 0. So not including the endpoint here, so -4 to -3, it is positive. And then it's also positive from 1 and then to forever because it goes up, 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 up. Notice no brackets there. So one more polynomial. We got a nice quadratic here. It's not in standard form yet, but it's about to be. And I think this does factor pretty nice, so yay. How about we do a +1 here? No. Yeah, that'll work. -2. 3 minus 2 is 1. Got it. All right, so this x-intercept is 2/3, and this x-intercept is -1. Yeah, which makes sense when I look at the picture. Someone already gave me a picture on all these. That must be Mrs. Hoffbauer. She's so nice. All right, so I can tell from my graph, but I like to, I'll go ahead and write them as a sign change chart. I don't actually have to plug them in because I can see on the graph whether they're positive or negative. So this is the ordered the x-intercept of -1. This is the x-intercept of 2/3. And I can see from my picture it's a positive function yonder, negative function right here, and positive function right there. So moral of the story is, for these polynomial inequalities, if it's on my test, I'm not going to take your calculator away from you. So the first thing I would do is I would get a picture of it. I would kind of use that to guide my next step. So if I notice there's rational zeros, I would find them through algebraic methods. If they look irrational and funky and things I can't find nicely, then I'm going to have to do quadratic formula if it's a quadratic or whatever. I would probably set it up as a sign chart, but I would actually use the picture to figure out whether it's positive or negative, rather than me manually plugging in numbers that are less than -1 and so on and so on. You sure could, or you could just go to your table or trace or whatever. Anywho, I need to finish this problem. When is it less than 0? Well, that was between here and here. Not equal to 0, though, so your interval is -1 to 2/3. Lovely. All right, so then on the back of your notes, this is where it gets crazy. So now, my face in the middle. Now we have a rational inequality. Because they're not polynomials. These are going to be our rational functions that have asymptote. So now when I'm talking about where are my critical values, it's not just 0 of the function, although those are important. Also, vertical asymptotes are going to be important. Okay. Or, yeah, asymptotes, yes. where's my function undefined is basically how we're going to say it. So this particular question here, where am I at here? Yep. So the sign change would be at any point of discontinuity as well as all the zeros. This is not going to be fun, guys. All right, so some wonderful person did this problem for us kind of halfway, and this is not the one on your notes, but it is a rational inequality. What you have to do, though, is it's not in rational form where I can see any discontinuities easily. We have to put it together in order to find the x-intercepts. Because if you remember, the way you find x-intercepts, you take your numerator and you set that equal to 0, and then any discontinuities that you're looking for will be our denominator set equal to 0, because those would be our vertical asymptotes. All right. I'm not really excited about this. Sorry. I'd be more thrilled. Again, you have a graphing calculator, and frankly, we have really nice ones nowadays. These TI-84 color edition ones, they give beautiful pictures. So if you're in a position where you can use technology to kind of assist you, at least, use it. But if you're on the half of your SAT test that's no calculator, or you're in a calc class where you have to do this by hand because the nature of the question demands it, we have to be ready for that, frankly. So this is pre-calculus, so we gotta get ready. All right, so here, I think the next screen. Lovely. All right, so we're going to take that new form of our rational equation, the one that's all simplified together into one fraction. And it says, notice that if you set your numerator equal to 0, you get 4/3 as your x-intercept. And we have to kind of notate what kind of a 0 or a discontinuity we're talking about. And then our discontinuities for our denominator are at x equals 6 and x equals -1. So what we're going to do on the sign change chart is we're going to put these critical values down in relative order again. However, we have to kind of mention what they are. So like this one here is an asymptote, this is an x-intercept, and this one here, is an asymptote. So the equal to symbol becomes really critical here, because if I say when am I equal to 0 and I'm looking at an asymptote endpoint, you are not actually equal to 0 on the asymptote. We'll get to an example of that in a second. Some beautiful person taking the liberty of giving us a picture of what this function looks like as well. So there he is, and you can see those 3 points in which your function does something weird. And they want to know, I already forgot the whole question. When is your function greater than 0? There we go. So on the sign change chart, and they manually plug some stuff in, but since they already have a picture of it, let's kind of verify with the picture. Before you hit -1, see how the function is below the x-axis? So it's negative. And then for the next part of the function between -1 and 4/3, which is right here, notice the function is up here, so it's a positive function. Now these do not necessarily alternate the same way that Polly's did, so be careful. So between 4/3 and 6, that's from here to here, so that's underneath, so it's negative again. And then up here, this branch is positive. So where was our function greater than 0? Now in this case, because it doesn't have an equal to symbol, it's parentheses all the way. So greater than 0 would be from -1 to 4/3, and then 6 to infinity. So I didn't have to worry about, is it an asymptote or is it an x-intercept, because they were all parentheses in that case. Note, a rational inequality can sign change at any point of discontinuity, so you have to worry about both the numerator and denominator zeros for these rational functions. Okay, so because of that, we saw in that last example, they had an addition of 2 rational pieces, and they had to get common denominators to add them together. So as the U, folk. All right, so here the common denominator is x minus 4 and x plus 1. So like this side over here had to be multiplied by an x minus 1 plus 1 plus 1. And then this side over here had to be multiplied by an x minus 4. And the common denominator was set up from the get-go, but the numerator is the result of us simplifying this blue box I just highlighted here. So like 2x plus 2 plus 1x minus 4, and then we get 3x minus 2. So that's where this number came from. Now that it's in this really pretty rational form, I wanted an eraser. Now that it's in this really pretty rational form, I can find my critical values where I set the numerator equal to 0, and I set my denominators equal to 0, and I find 2 asymptotes and 1 x-intercept. And then again, some beautiful person came by and told me what it looked like because they gave me a screenshot of my calculator. Isn't that beautiful? So using our sign chart, writing our 3 critical things that we just found in relative order. Let's see, -1, and then 2/3, and then 4. So I can see from my picture here, before -1 hit, we are underneath the x-axis. So we are looking at a negative function. Between -1 and 2/3, where am I at? Yeah. So 2/3 is like, must be here somewhere. It's not the greatest picture, but it's better than nothing. So the function is positive. Between 2/3 and 4, the function is below the x-axis negative, and then after 4, that branches back up in the positive region. So I already figured out what the question was. It said greater than 0, I believe. So again, we don't have to worry about brackets in any case here, but the places where it's greater than 0 are right here and right here. So from -1 to 2/3, union, or to infinity. I think the next one's going to have the weird asymptote bracket issue. Oh, no, it doesn't. Darn it. Okay. Now this one looks so simple, right? It's like, oh, look at that cute 30 fraction. But remember, we have to compare it to like greater than or less than 0. So first thing we're going to have to do is bring the 3 over by subtracting it. And then realizing that we're back in trouble because we don't have any common denominators right now. So what if we were to multiply this fraction by x plus 2? And that would give us a common denominator of x plus 2. But your numerator, oh man, be careful here. My Algebra 2 kids screw this one up every time. This is a -3 that they're distributing. So I have x minus 1, and then a -3x, and then careful, that's a -6. Is greater than 0. So after a little bit of work here, that ends up being -2x minus 7 over x plus 2 is greater than 0. Now, it doesn't have to look super pretty. Just this is a 2-step algebra problem when you go to solve the numerator and denominators. So like here, when you set your numerator equal to 0, you get an x-intercept of -7/2. I should be able to do that a little quicker, huh? And then here, you get a vertical asymptote at x equals -2. So the 2 critical points that we're finding are those 2 critical points. So if you want a sign change chart, that's cool. -7/2, remember, is like -3.5. So that would come first on the number line. I have a party of a bunch of like 2nd graders behind me in the other room. Can you hear them? Sorry if you can. Rowdy. All right. So greater than 0. I don't really know what this looks like, but I don't think it would be too tricky for me to plug in a few numbers. I'm probably going to plug them into this version of the problem, though. Assume I didn't make any mistakes ever, huh? So I'm going to plug in something like really obviously over here, like, -10. So -10 times 2 is 20. 20 minus 7 is 13. So that's a positive number. Over -10 plus 2 is something negative. So positive divided by negative is going to give me a negative solution here. And then something nice to plug in between these two guys. How about -3? Does that sound like a nice easy point to plug in? Sure, Bruzo. All right, -3 times -2 is 6. 6 minus 7, something negative. And then -3 plus 2 is something negative as well. So negative over negative is going to give me a positive set of solutions. And then anything after -2 would work. So I'm going to go with my friend 0. Plugging in a 0, I get -7 over 2. So -7 starts something negative. So we did see some alternating signs there. And the places where my function is greater than 0 is from -7/2. You can say -3.5 to -2. I don't use any brackets because it did not say equal to. I didn't even have a picture of the poly on that one. But it was a real basic rational function, so you could have found one. Oh, finally, got the equal to bar. Okay. So we're going to subtract the 1 over, because even though it looks like it's real basic, it's not quite in rational form yet. And then we're going to realize, oh snap, we need to get common denominators. So I'm going to multiply this fraction by x minus 4. There are people out there in the world who can just get common denominators on these without doing the extra work. I am not one of those people. All right, x plus 2, and then be careful you're subtracting all this. So negative x, and then a plus 4 over x minus 4. So the numerator cleans up quite nicely. Just a 6. So we have 6 over x minus 4 is less than or equal to 0. So it turns out there is no x-intercept on this question, but there is a vertical asymptote at x equals 4. So as far as like change chart, 4 is the only critical point there. If I plug in something smaller than 4, like a 0 per se, I would have 6 over negative 4, which is a negative value. And then plugging in something larger than 4, like a 5, clever, 6 over 5 minus 4 is 1, so that's something positive. So where is my function less than or equal to 0? Remember, this number here is an asymptote. So I can't include this as part of my endpoint. Like I can't use a bracket when I get to 4 because it's an asymptote. So less than 0 would be this section here, but not including that endpoint there. So negative infinity to 4 with a parenthesis. Fancy, huh? All right. So be careful. Bad news, bears. We have no common denominator. So this has to be hit by an x minus 4, and this has to be hit by an x plus 2, which would give us the common denominator that I'm looking for. So x minus 4 plus, careful, 3x plus 6 over my new common denominator of x plus 2 times x minus 4. If you need a little work with getting common denominators, you can go back to my Algebra 2 playlist and look for something from section, oh gosh, I think it's 8.5. That's what it's called now. You just Google anybody's YouTube video on adding rational expressions is what you're looking for. All right, I digress. You know I wanted you to go to my video because they're the best. All right, so it's x minus 4 plus 3x plus 6. How does it simplify? 4x plus 2 over x plus 2 times x minus 4. This numerator does factor, but we don't have to worry about like holes in these problems that I'm going to give you. All right. If I set my numerator equal to 0, I would find an x-intercept at negative half, because negative 2/4. If I set my denominators equal to 0, I am going to get two vertical asymptotes at x equals negative 2 and at x equals 4. So 3 things on my sign chart that I got to worry about. If I put them in relative order, they are negative 2, followed by a negative 1/2, followed by a 4. And I am going to notate on my little sign chart here who's an asymptote and who's an x-intercept. So this guy here is an x-intercept, but this is an asymptote, and this is an asymptote. It's not going to matter for this question because we're going to use parentheses on everybody, but it's just a good habit for the rational functions. So if I plug in something less than negative 2, and you know, it doesn't really matter which version you plug it into, but obviously this one looks a little easier to plug into. So I'm going to plug in like, I don't know, a negative 5. So negative 20 plus 2 is something negative over something negative times something negative, which is something positive. So negative over positive is a negative number. And that's the kind of thing you'd be doing. So like here, I might plug in the number negative 1. I'm going to cheat because I already did this times in fact. So it toggles to positive next, and then negative, and then positive again. So again, you can take a $150 calculator if you want to just graph it. That's fine, but finding these values very specifically is super important. And frankly, I think it's easier to do algebraically. They want to know where this function is greater than 0. So I'm looking for this interval and this interval. So that's from negative 2 to negative 1/2. And also 4 to infinity. It doesn't stop. And then the last one, my favorite one, because it's exciting. Oh boy, bad news again. We need to move that 1 over and then get common denominators. So I have a 1 for now, but now he's going to get multiplied by that common denominator. So that way we can write it as one rational term. So distributing a 1, boring, and then adding your like terms, it's 5x minus 1 over 3x minus 2. Now be careful, like nothing cancels here. Only factors and whole terms can cancel, so watch out for that. I want to know where this function is greater than or equal to 0. So this is going to be one where I do my sign chart. It's going to be very important that I notate who is an asymptote and who's an x-intercept. So let's find my x-intercept by setting this numerator equal to 0. So I have an x-intercept at 1/5, which is 0.2 if you want a decimal. And I have a vertical asymptote at x equals 2/3. So on my sign chart, putting that in relative order, 1/5 is smaller, so 1/5 and then 2/3. And then again, notating that this guy here is an asymptote. So if I include this endpoint, I can't. I have to use a parenthesis here. This, however, is an x-intercept, and it can equal 0. So using a graphing calculator and looking at the picture, or plugging in numbers like 0, my favorite number, plugging in a 0 here would be negative over negative, so it gives you a positive number. Plugging in something in between here is going to give you a negative, and then plugging in something large like 10 is going to give you a positive number here, because it's positive over positive. So where is my function greater than or equal to 0 would be this interval, but watch, remember, equal to 0. So we can count this one, cannot count that one. So negative infinity to 1/5, including 1/5. Jumping all the way over to not including it, but 2/3, because it's an asymptote, to infinity. Good time. All right. That is actually the last lesson in chapter 2. So the next unit's my favorite. Very excited. All right, see you in a bit.